Hey Calculus class! Tonight we're going to learn topic 39, the trigonometric integrals. So let's do a little quick review of some of our trig identities. So we have our Pythagorean identities, which are sine squared x plus cosine squared x equals 1. We have the secant squared x equals 1 plus tangent squared x. And we have cosecant squared x equals 1 plus cotangent squared x. Then we have the double-angled identities. That would be sine 2x equals 2 sine x cosine x, which we could rewrite as sine x cosine x equals 1/2 of sine 2x. And the reason why we would do this, you will see shortly. Then we have the good old cosine 2x, which has 3 different forms. Cosine 2x can either equal 2 times cosine squared x minus 1, or it could equal 1 minus 2 sine squared x, or it can equal cosine squared x minus sine squared x. And we can rewrite the cosine squared x as 1/2 times 1 plus cosine 2x. Or we could rewrite the sine squared as 1/2 times 1 minus cosine 2x. These are what we call the half angle identities. And for these type of integrals that we will be doing shortly, you do have to know these identities. The AP test does expect you to know them. All right, some trig integrals that you also need to make sure that you know. First, we have the integral of tangent x, which is equal to the natural log of the absolute value of secant x plus c. The integral of cotangent x dx, which is equal to the natural log of the absolute value of sine x plus c. The integral of secant x dx, which is equal to the natural log of the absolute value secant x plus tangent x plus c. And the integral of cosecant x dx, which is equal to the natural log of the absolute value of cosecant x minus cotangent x plus c. All right, so what we're going to be doing in this unit is integrating powers of trig functions. So that means that we will be looking at functions in the form of these possible 6 options: sine to some nth power, cosine to some nth power, tangent to some nth power, cotangent to some nth power, cosecant to some nth power, and secant to some nth power. We will be needing to rewrite the functions so that you can use one of the trig identities that we just reviewed a few slides back. All right, so let's look at an example. All right, so we have the integral of sine cubed x dx. Well, we can rewrite sine cubed as sine times sine squared x. And we have a trig identity that we can rewrite sine squared as. And that is the Pythagorean identity, that sine squared can be rewritten as 1 minus cosine squared x dx. And the reason why I chose that is because now I'm going to use u substitution so that when I take the derivative of u, I have my derivative in the integrand. So you should notice that we're going to want our u to be cosine. So that means my du is negative sine x dx. And you'll notice that we have a sine x dx here, just no negative sign. So that means I'm going to have to substitute in a negative du for sine x dx. So now when I do the substitution, I substituted in the negative du for sine x dx, and I substituted u in for cosine. So now I'm integrating 1 minus u squared, something that is much more simpler to integrate. So I'm going to go ahead and integrate. And I get negative times the quantity u minus u cubed over 3 plus c. And then, of course, replace u with cosine. so that I now get negative cosine x plus cosine cubed over 3 plus c. And I also went ahead and distributed that negative sign. All right, why don't you go ahead and see if you can try the second one on your own. All right, let's see how you did. So you should have rewritten cosine to the fourth as cosine squared to the second power. And you could have written cosine squared times cosine squared. It's the same thing. But the reason why I'm going to do this is because I have that half angle identity where it is 1/2 times 1 plus cosine 2x. So I'm going to use that to replace cosine squared. So now I have the following. And I can go ahead and use my exponent properties and distribute this power of 2 to the 1/2 and to the 1 plus cosine 2x. So that I get 1/4, and since that's just a multiple constant, I pulled it out. And now my integrand is 1 plus cosine 2x squared. Now, going back to some, hopefully something that you remember in Math and Now, is that we can expand this so that it then becomes something similar to a polynomial. So now I got 1 plus 2 cosine 2x plus cosine squared 2x. Now, after I went ahead and expanded out this binomial, I now can use this cosine squared x half angle identity because I have a cosine squared 2x, and I can apply this, but instead of having just a 2x in this cosine, I'm going to have a 4x. So that I now get the 1/4 times the integral of 1 plus 2 cosine 2x plus 1/2 times the quantity 1 plus cosine 4x dx. Now I'm going to go ahead and distribute this 1/2 through, and at the same time I'm going to combine this 1/2 with this 1, which gives me the 3/2, and then everything else is the same. Now I can go ahead and integrate, and I can now integrate each term individually. When I integrate the cosines, I'm going to have to use u substitution. Now for this PowerPoint, I did not put out each work for the u substitution, but the antiderivative of 3/2, that's just 3/2 times x. Now when I do the integral of 2 cosine 2x, my u is 2x. So that means my du is 2 dx, and I have a 2 here. So that means I'm just integrating cosine u, which is just sine u, and my u is 2x. And then same thing here. My u is 4x, so that means my du is 4 dx. I don't have just a 4, so I'm going to have to multiply this one by a 1/4. So that 1/4 multiplies the 1/2. That's where I get the 1/8. And then the cosine, the antiderivative of cosine u is sine u, but u is 4x. And I can go ahead and leave it like that. All right, let's try one with tangent. So for this one, I'm going to go ahead and rewrite tangent cubed as tangent x times tangent squared dx. And I can use the trig identity on the tangent squared x, or sorry, the Pythagorean trig identity, which is secant squared minus 1. And I can go ahead and distribute this tangent through, so that now I have tangent secant squared x minus the integral of tangent dx. And I can break this up into two separate integrals. For the first integral, I'm going to use u substitution. My u is going to be tangent because my du is secant squared dx, and I have the secant squared dx. And then for the integral of tangent, that is one that we did with u substitution a few days ago. So when I substitute in for the first integral, I'm going to integrate u du, and I've already integrated the tangent, which is the natural log of the absolute value of secant x plus c. And so when I integrate u, that means I get u squared u squared over 2, replace u with tangent, so that I get tangent squared x over 2 minus the natural log of the absolute value of secant x plus c. All right, let's try this one. The integral of secant cubed dx. So I can rewrite it as secant times secant squared. Now for this one, you have to actually use integration by parts, because I'm going to let u be equal to secant and dv be equal to secant squared dx. And so that means my du is secant tangent dx, and the antiderivative of secant squared, well, that's tangent. So now when I set up the integration by parts, I'm going to multiply the u times v, so secant times tangent, minus the integral of v times du, and so that gives me secant tangent squared dx, since I have two tangents here. Now when I go ahead and integrate this integrand, I'm going to have to now use one of my trig properties. And the one that I'm going to use is the Pythagorean identity for tangent squared, which is secant squared minus 1. Now I'm going to go ahead and distribute this secant through and split it up into two separate integrals. Now keep in mind that this negative comes along with that secant, so that's why this became a plus. And notice here that I have the integral of secant cubed x dx in what my answer should be, and that's what I'm trying to integrate. So like we did yesterday with integration by parts, since this is one big equation equal to the integral of secant cubed x dx, I can bring this integral over to this integral, so that now I have two integrals of secant cubed x dx equal to the secant tangent x, and we've already know the integral for secant, which is the natural log of the absolute value of secant x plus tangent x. And then of course, to solve for the integral, divide by 2 and tack on your plus c at the end. All right, let's try definite integral. So the trig property for this one is the half angle identity for sine squared, but the inner function is a 2x, so that's why there's a 4x here. So this is what I'm going to integrate. And I can go ahead and integrate each term separately, so that 1/2 is going to multiply everything. And then the antiderivative 1 is x, and I'm going to evaluate that from 0 to pi over 2. Now when I integrate cosine 4x, I'm going to have to use u substitution. So my u is 4x, du is 4dx. I do not have a 4, so that means I'm going to have to multiply by a 1/4. Now I can go ahead and substitute in the u's. At the same time, I went ahead and changed the limits. So when I plugged 0 in for x, I got u equals 0. When I plugged pi over 2 in for x, I got 4 pi over 2, which is 2 pi. And then at the same time, I also went ahead and evaluated the x from pi over 2 to 0, which just gives me pi over 2. Now I can go ahead and integrate the cosine u. At the same time, I went ahead and distributed that 1/2. Now when I go ahead and plug in 2 pi and 0 for u, you should get pi over 4. Well, I hope you enjoyed all of this trig stuff, and I definitely understand that it's hard because it's really, really difficult to figure out which identity you have to use and when. And unfortunately, there's no trick to know how. It just takes practice and knowing all of your trig identities. All right, I will see you in class and have a good night.